Good morning.
Good morning.
I still haven't done my 2 recorded lectures, which tells you how my week is going. We've all had weeks like that, right? But the modules are up. The assignment for this week, though, I was going to have 2. One was worth 20 points and then the report worth 40. And I'm not going to do the 20-point assignment. And what I'll do at the end of the semester is, everybody just gets 20 points. So that way you can't, you don't have to worry about it. I'm worried about workload on you guys, and I don't have a strong judgment on that. I don't think this class is too bad, but it's hard to tell. The report, the assignment that's out there is to do a short report. Go online, find a program optimization, and give a brief description of it. I'm thinking page, 2 pages, something like that. But, normal professional writing rules apply, where you need to have proper citations, references, that kind of thing. By the way, some people do references. They put the references in at the end of the report, but they don't cite them. Citing them means when you use that reference in the body of the report, you actually have to mention it at that point in your text. So please remember, do both a citation and a reference. Please don't use, I don't care what format. Yeah, format's fine. Please don't use web references. You can find texts and you can find PDFs of texts online. You can find real articles that exist independently of the web. Okay, let's talk about the program dependence graph. And again, this comes under the category of good stuff to know. I'm not going to give you an explicit test on it, but it's a widely used representation. And yes, that would work, Casey. Yep. Because those exist independently of the web. Yep. And because master's students are always looking for a thesis topic, they will grab a program optimization as a thesis to try to develop a new one or to try to put an efficient twist on an old one. I think that, again, the standard book, if you look up Dragon Book, you'll find the standard book on compilers, and they have quite a few optimizations in there. If you're one of those people who like to look at things and say, wow, that's clever, I recommend 2 places. One is program optimizations, because it's like, wow, that's clever. And the other is chip design, just seeing how they design chips to make them faster. Really clever, cute mathematical tricks going on. Anyway, the idea behind the program dependence graph section of the course is to round out your knowledge and give you a view of a widely used intermediate representation. And also to remind you what graph structures do. Graphs are the most flexible, most descriptive form of data structure, and they are used everywhere. So the more you learn about graphs, the more valuable you become as an employee to somebody. I've been pushing for a graph course in our curriculum for some time, and we just don't have the resources to pull it together very well. So hopefully one day we'll fix that. All right, so the idea is if you look at a program, there's a program, forget the graphs on the right for now, but that program on the left with the 9 lines, we talked about def statements and use statements. Defs are where you assign a binding from a variable to a value. And a use is where you use that. And the sequence of these things sets up relationships called dependencies, where one statement is dependent upon another. So basically the use statement is dependent upon the def statement. So if we look at statement 2, where we say y equals some kind of input, and then statement 3, it says if py, that's kind of my shorthand for for a Boolean function of y. Then statement 2 is the def and statement 3 is the use. And you can see there's some kind of dependency there. You can't do statement 3 until you do statement 2. So any kind of optimization that tries to flip the sequence of those statements is bound to fail. Similarly, if we look at statement 1, that's a def for x, and statement 4, that's a def for x, and statement 8, that's a use of x, then the question is, well, wait, where's the dependency there? Well, the dependency is on both, oddly enough, 1 and 4, because either one of those could flow, if you think in terms of data flow, either one of those could flow their values down to statement 8. So we had this notion of dependencies based on def use, but we also have dependencies based on multiple def statements. For example, let's say in statement 3, py turned out to be true, and we need to execute the statement 4, x equals 42. Then what value should show up when we do statement 8? You know, when we say z equals fx, the value should be 42 at that point, right? Well, if you swap the sequence of statements number 1 and 4, you would get the wrong value. And remember, this is what compilation optimizations are all about. What can we move around? What can we swap out? If you swap the sequence of 1 and 4, that would be a problem, because we needed 42 to go there. But if statement 1 executed after statement 4, then the value of the whatever was input would be there instead. And again, you may be asking, well, surely it wouldn't be swapped around. Surely the code is executed as written. No, the code is not executed as written. The optimizer swaps things around, but there are limits to what can be done. And so far we've identified 2 limits. One is the limit of, I can't do statement 3 until I do statement 2. And the other limit is, if both statement 1 and 4 execute, they have to execute in that sequence in order to make sure the correct value goes to statement 8. Okay, those are data flow dependencies. What about control flow? What about control dependencies? Well, we can ask, when does statement 4 execute? Statement 4 is either going to execute or not execute based on the results of that Boolean test in statement 3. So we say that statement 4 is control dependent on statement 3. Oh, and by the way, I only put the continue statement on line 6 in there so we wouldn't have an empty else block. Statement 6 is also control dependent on statement 3. So control dependence is asking the question, what statement is it that, which if statement is it that tells you whether you will or will not execute? That's the intuitive notion of control flow. When you put those together, you actually get something called def order, which is when I get to statement 8, again, let's say I can get these things done in any sequence. Then how do I know when I am allowed to do statement 8? If statement 1, 2, and 3 both execute, can I do statement 8 yet? And the answer is, it depends on the result of statement 3. If statement 3 is false, if py is false in statement 3, then the value for x that we got in statement 1 is the correct value for 8, and we can go ahead. But if py resolves to true in statement 3, then we have to bring the value of 42 down to statement 8. So basically statement 8 is not control dependent on statement 3 because it's going to execute no matter what, right? It doesn't matter what the result is. Statement 8 is going to execute no matter what. But the value that it uses is still dependent on statement 3. So we have something called a def order dependency. It has been proven that if you respect those dependencies, you can do whatever you want to the program and you will not change program input-output behavior. And remember, that's how we're defining what a program is based on its input-output behavior. So other than those rules, I mean, as long as you respect those rules and don't violate those rules, you can do whatever you want in the optimization phase, and you still will come up with a valid program that meets the original programmer's intent in terms of input-output behavior. So what changes? If input-output behavior doesn't change, what does change? Computation cycles, memory footprint. Right? That's the whole point of optimization, right? Is to either reduce the computation cycles, or you can optimize to reduce the memory footprint. Normally they focus on computation cycles. Now, one reason that this doesn't get as big a share of the curricula in modern computer science degree programs as it used to. Number one, as I said before, you probably won't create a compiler from scratch. There is software to create compilers, so that software does exist. So, you know, it is unlikely in your career you will create a brand new functional Turing computable language and need to create a compiler for it. However, on the other hand, you almost certainly will be creating code that parses data structures. So number one, the likelihood that you're going to build a compiler from scratch is pretty low. That's one reason. Number two, people don't focus on optimizations as much as they used to because chips are fast and memory is cheap. So now people are thinking in terms of building code, build it inefficient, but build it more readable for human consumption. Now, somewhere in there is balance. So you still have optimizations that are performed by compilers. Even Java, you know, they don't compile all the way to machine code. They compile down to bytecode, if you recall. But they perform optimizations along the way. And then while the Java virtual machine is running the bytecode, it still performs what we call the keyhole optimizations while the bytecode is running. And you can compile beyond bytecode all the way down to executable code. And there's such a thing called a JIT, a just-in-time compiler, where when you're running your Java code, if the Java virtual machine has a strong case that this can go much faster if I just compile everything to machine code, it will do that. And there's something called Java hotspot technology actually that does that. If you're in a loop and you're looping for a long time and it's in bytecode, the Java virtual machine might say, "Ah, the heck with it. I'm going to compile this thing," and actually compile your loop and then run the rest of the loops without doing the constant conversion from bytecode to machine code. The advantage to that, by the way, is that the parameters of the loop are already known at that point, and the compilation to executable code can occur in a very efficient fashion because you take advantage of the specific things. All right, let's talk about these dependencies again. We're going to worry about definition 6 here. These are stolen from my dissertation. Output dependence, B is output dependent on A, if and only if the execution of A occurs before B, and both A and B assigned to the same variable. That's the case down here with statements 1 and 4. If they both execute, we have output dependence because if 1 is supposed to come before 4, before you do any messing around with the sequence of the statements, then no matter how you mess around with the sequence of statements, 1 still has to come before 4. Control dependence, that's the one where we say, wait a minute, which specific if Boolean test is the one that tells me that I'm going to execute or not execute? So control dependence, line 4 is control dependent on line 3 because it depends on the outcome of the Boolean function py, and line 6 is output dependence on 3 because it also depends on the result of py. Now, clearly, this is a really, really simple piece of code here, but you can imagine, I mean, you've all written programs with quite a few if then else statements in them, and you could go through and look at your code and say, okay, this if then else statement is telling me that these specific statements are going to execute or not execute. There's your control dependence. Now 8 and 9, 1, 2, 3, 8, and 9 are going to execute no matter what. So they are not control dependent on anything. Flow dependence. B is flow dependent on A, if and only on A, if A is a def and B is a use. So now you have to say again that this would be the statements between, whoops, I'm sorry, I'm going the wrong way. This is the dependence between 2 and 3. Statement 3 is flow dependent on 2 because you can't resolve PY until you have a value for Y. So 3 has to happen after 2. And then lastly, the def order. It's a little more complicated. Okay, def order dependent on A. Both A and B are def statements. A precedes B, and there's some statement C that is both flow dependent on A and B. Oh, that's 1 and 4. Statement 4 is def order dependent on 1 because they both supply a value for X, and both of those values potentially could flow to line 8. Now, in any given execution run, only one of those will flow, but remember our discussion about static and dynamic binding, we don't know in the static case. We can't do that analysis in the static case. So the only way we know is in the dynamic case. So in terms of being conservatively correct, we can't swap the sequences of those statements. 1, 4, and 8 have to happen in that sequence. And using those 4, forget anti-dependence. Using those 4, if we, again, as long as we respect those 4 dependencies, we can do whatever we want with the program. And so using those 4, people can create a graphical form that represents these things and then create what's called a program dependence graph. Now you know why it's called a program dependence graph. It's showing the flow dependence, the output dependence, the def order dependence, the control dependence. And the way I did mine are triangles are the if then else's. It's the Boolean test for if then else. True on the left, false branch on the right. Rectangles are IDEF, that's initial definition. Def statements, assignment statements. And then the circles are the output statements. Basically what you say we worry about computation, but we don't worry about IO so much with program dependence graphs. So every statement every program is assumed to terminate, and it terminates with output, which is basically saying you have a final version of the store. Solid lines for control dependence and red dotted lines for flow dependence. And now we can take that section of code on the left and convert it to graphical form. There's 2 forms of the graph that are given, and that's because it was relevant to the topic that I have in my dissertation, but I want to focus on the one on the right. I'll talk a little bit about the one on the left. Basically, the program is going to start. That's a given. The program is going to start. So I treat the start of the program as an if statement that has the constant value true as its predicate. It's going to start. From there, we look at, okay, what statements are definitely going to execute? If we look at what statements are definitely going to execute because we've started this program, we can look on the left and identify that's going to be statements 1, 2, 3, 8, and 9. And if you look at the nodes, the control nodes, the solid arrows that come off of the start, you get 1, 2, 3, 4, 5 nodes that correspond to statements 1, 2, 3, 7, and 1, 2, 3, 8, and 9. Everyone see that? So I have X input, that's the initial definition for X. I have Y input, that's the initial definition for Y. I have PY, well there I need that statement is definitely going to execute. So there's the Boolean test in statement 3. Then there's the statement for establishing Z, that's statement 8, and then the end statement, which is the ninth statement, is there. So those are all the statements that are saying if you start the program, that's definitely going to run. Those are definitely going to run, so they're control dependent on S. And then the only ones that are control dependent on P, I omitted this continue statement in line 6. The only one that's control dependent on P is statement 4, x equals 42. So statement P, x equals 42, occurs on the true branch of that if then else statement. So those are all of our control dependence. What about flow dependence? Well, I can't do statement 3. I can't resolve P until I know what Y is. So if I look at I_def Y, there's a dotted line going to the node for P. That's a flow dependence. And I can't figure out what value to put in for X on statement 8 until I do some other tricks. Now, what we talked about in the code is that could come from 1 or 4. And there's 2 forms of a program dependence graph. The traditional way is this way, where they have something called a phi function, which will resolve which of those 2 values go there. Semantically, some people have issues with it because it wasn't clear how that resolution was done. And there were actually theoretically still errors that could be made. So another way to do it is to put this extra node in here where you just say x equals x. So if you look at what happens, when you look at what happens in terms of the flow graph, in terms of control dependence, either x equals 42 or x equals x, only one of those can execute because P can't be true and false at the same time. So when we run through the program one time, P is either true and we get x equals 42, or P is false and we get x equals x. And then both of those flow to the use node. And then the rules for, okay, when am I allowed to execute the use node? I'm allowed to execute the use node when I have one value for X and I have no more incoming flow nodes. So for example, if I'm working with this graph, once I resolve P, if P is true, I'll destroy that X equals X node. And now I only have one value flowing in for X. And if P equals false, I'll destroy the X equals 42 node. And then I only have one value flowing in for X, which is the X equals X. And the name for that is a single flow to use. I know SFU is used for other terms, but it's single flow to use in this case. Now, why is this a widely used graph? First of all, remember what we said about intermediate representations. One of the good things an appropriate intermediate representation should do is when you move the code from the source code to the intermediate form, it should be independent of the programming language. So when you're looking at, in this case, the program dependence graph, you should not be able to tell what the incoming language was. What the source language was. So this thing, it's a Pascal-like language, right? It's a made-up language. But you could see that if you program these kinds of statements in C, and you program these kinds of statements in Java, and you program these kinds of statements in Python, you would get exactly the same graph no matter what. So that's one thing that's helpful. It removes your dependence from the source code, from the language. Which means if you develop an analytical tool for the program dependence graph, you've developed an analytical tool basically for all programming languages. Now, do people do analytical tools? Yes. This is clearly a small piece of code, therefore the graphs are very small, but you can take larger graphs and then you can do what's called program slicing. And program slicing asks 2 questions. If I look at a statement, how can I determine what previous statements might affect it? For example, here I am in line 8, z equals fx. I output z, and it looks wrong. That's the wrong answer. How could I possibly figure out where that is in terms of debugging? Oh, I go here on the graph. Statement z got its value for x from 2 nodes, so I can do what's called program slicing. Let's see. That x equals 42 node, that could possibly be part of my problem. That x equals x node, that could be part of my problem. Oh, but where did x equals x get its value? From this idef x node. So now instead of looking at the whole code, I only have to look at 1, 2, 3 nodes to see where my error could come from. Now in this, what, I've got 9 lines of code, one of which is just a bracket. So I've got 9 lines of code. Yeah, cutting that down to 3 is no big deal. What happens when you've got hundreds of thousands of lines of code? A program slice will tell you which lines of code to focus on to see where the error might be coming from. And then you can ask the other direction. What lines of code might be affected? I go forward on the graph. So you see what we're doing is using the graph structure to move up and down. I think hopefully everybody's taken the CS315 data structures and algorithms class. And if you did, you talked about trees and tree traversal. And we know how to traverse trees. We know how to traverse graphs. It's an easily performed thing. So this notion of creating a program slice, if you were to try to do it in the text form, is very difficult. If you try to do it in the graph form, is really easy, because all you're going to do is look up if you're going backwards in time, backwards in the program, you're going to look up the program statements, up at the ancestors of a particular node in the graph. And if you want to make a slice forward, then you go forward in the node of the graph. You go to the descendants. And again, graph traversal is a well understood problem. So that's one form. And then another form is people do use this for optimization, because look at the nodes. I have all these nodes that come off of F, idef Y, X, end Z, F of X, Z, and P. In terms of control flow, they can all be performed at any time. So I'm starting to say, look, I had these 5 statements, and now I can start to swap the order of these statements around. What limitations do I have? Well, no matter where I put idef Y, I have to put P after it because of the flow dependence. But I do have, in this case, I think we can only do idef Y and idef Z are the only two that can truly be swapped, right? But since we've taken the sequential structure away from the program, the optimizer has more freedom to manipulate the program statements. This is very similar to, remember when we did derivations? So we had a grammar and then derived this string, and that derivation was done in a step-by-step fashion. And there were multiple derivations that you could do for one string. And then later on, we said, okay, now here's a grammar and a string. Let's make a parse tree for it. And you only got one parse tree. Why? Because the parse tree took away that sequential nature of the operation. And the PDG is doing the same thing here. It's taking away the sequential nature. So even though I have different programs in terms of maybe they have the same lines of code but different sequencing, you're still going to get the same program dependence graph. Okay, that's my talk on program dependence graph. We have plenty of time left, and I'm okay closing early, but since we have plenty of time left, what is confusing right now? What do you need to know to get the homework done, or just to clarify some points?
I've yet to take a look at the homework, so.
Okay, the homework is just to go find an optimization online and write a report about it, describe it. Yeah. And again, when I say report, I'm losing the word a little bit loosely. I'm expecting like a 2-page kind of report. And when they're that small, you don't need a title page. You certainly don't need a table of contents. Having some figures are probably helpful, right? Having pictures to talk to, that's usually a good idea, right? Like that kind of thing. That's straight from Wikipedia. Yeah, I know, I used Wikipedia. Having pictures, that can be helpful. Having Usually they'll have some algorithmic description of what the optimization is. Okay, so don't do loop unrolling, don't do constant propagation. Do some other form.
And where should we start looking for like these optimizations?
I think, well, a couple things. You can look, I would look on Google Scholar, first of all, not just Google, but you can also, you can look for compiler textbooks. And then if you can find a PDF of a compiler textbook, or you can, you know, if you're going to a physical library, get a compiler textbook, they will all contain optimizations. And if you don't want to do that, you can look up, you know, common compiler optimization techniques or something like that. But often what you'll find, you know, again, on your first form of a brute force search is something that just a web page or a blog or, you know, Wikipedia. Again, Wikipedia is fine. Not that you use Wikipedia directly like I did. You actually should use the references that are in Wikipedia. And if you Google, I think the authors of the Dragon book, the original authors were Aho, Sethi, and Ullman. But if you Google Dragon book, Dragon compiler book, I'm sure there are PDFs of that online, some of which are probably even legal, and you can look through there. So either Google about program optimizations or Google about compiler techniques or compiler textbooks. If you go into Scholar, you will find, as Casey pointed out, you'll find textbooks and papers, which is going to be really what you want.
Okay, and then just basically reiterate.
Yeah. This is where this is where tech writing gets hard, because you can't plagiarize, but you have to say exactly what they said, right? So that's a tough. That's the hard part about tech writing. If you use their figure, I'm fine if you want to use, you know, if they have a figure describing stuff and you use it and cite it and, you know, that kind of thing, as long as you're using your description of how to interpret it. Okay. Oh, some of you guys asked some questions on the last homework.
Yeah, that was a tough one.
Yeah. So someone asked a question on Friday and I didn't get around to answering it till yesterday. And, you know, the grader's behind schedule. I'm not going to worry too much about late assignments right now. So I'm going to, if I remember, I'll push that date back a little bit, so that if you turned in something and you weren't sure about it, you want to hand it in again, I'm fine with that. Because it's not like we're, you know, hungry for things to grade right now. There's a pile right now. The reports, by the way, I'll grade rather than having Michael do it. He's already busy enough, and I wanted to look at your writing. So. Okay, anything else? Okay, guys, always a pleasure.
Thank you.
Thank you,
Bye.
Professor.
Thanks.